Hello, this is Rafael and R.S.R from Athens. Today we will present to you the final project for CS50 Python, which is called Reference Sequence Reconstruction, or R.S.R for short. R.S.R essentially takes a nucleotide sequence as input and it then proceeds to generate a population of random sequences, similar sequences, which will or will not reach the reference sequence. More specifically, it takes either an NCBI accession number or a nucleotide sequence as input, and it then creates the population which was mentioned before, and it mutates the population according to some arguments that the user gives. Now, as with any program, I would first run the program, of course, with the -h tag, so that I can see the arguments that are available to me. And if I do just that, I get all the available arguments to me. And as you can see, there are quite a few of them. Now, of course, someone that is other than me, of course, would run this program with the default parameters, which would be with no arguments at all.
Which is where I come in, because the first thing that I would probably do is, before I run -h, is I would probably just run the default run of any program. I would blindly trust whoever's written it to do whatever it is that the program does. And if we run it, we get a little bit of a nice printing statement. It's going to take it a couple of seconds because it's got a lot of number crunching to do. And okay, it tells me how long it took, and it tells me there's two different files that I can look at for the results. So there's results.txt, which is this file, and it's essentially just a log of everything that's happened. Every person's sequence throughout the generations, who mutated, how, new sequence, the crossings, all the different things that happen in the run. And it's telling me that I've got a graph. So let's look at it. It's essentially what the results.txt is, but in graphical formation or notation, or however you want to call it. We've got on the top, the pinkish line is the population size in each generation. The exact same format of graph is underneath, but instead of the population size, it's got the reference similarity or identity of the two sequences. So we compare the sequences of each individual in the specific generation to the reference sequence that has been given, and we average that out and we get the average. Now look, it's not that good. It doesn't really go anywhere. So I would start playing around with the flags in order to make it do a little bit of a better run, but unfortunately, I haven't had that much experience with the flags, and I write one of the ones that aren't in the help section. So I get the nifty help section again to tell me that I've written something wrong, and a little print statement at the end that tells me we don't really know what this does, so try running again. And I try to run it again, and this time I get the right flag, but the input value that I give it is 50.5. Now, we can't really have a population with size 50.5 because you can't have half a person. I try to run it again, I finally get the flags correctly, and if we give it a second, okay, it's going to tell me that the population died. So there's a little bit of a randomness aspect to the program itself, that the population could die at any moment, regardless of the flags that you've given it, to be honest with you. But now that I've played around with the flags a little bit, first of all, I've changed the output spot that the folders are going to be at, and it's right here. It's relative path. So that's it's the same graph, it's just updated. And I've changed the accession number. LM, whatever this is, refers to an NCBI accession, so it went to the NCBI website, and it requires that you do have internet access at that moment. It took that sequence and it used it as our reference, so it's a different one than the base default run. I changed the rate. The rate is the mutation rate, so how much of the sequence changes every time a person mutates, how often that happens is different in this case. Size is the population size. Gen is the generation that it did, so notice that the graph ends abruptly at, what is this, 13? Generations, because the population died and it exits. If it had run for the whole duration, it would have done 50 generations. Previously, we had 100 in the default runs. And I've got the criteria in the drift that we're going to talk about later. I've got -v for verbose. So the reason it printed everything that was essentially going to be written to results.txt is because I decided to give the verbose flag. Moving on, anyway, I'm going to play with the new drift and criteria values. So the population died again. Drift refers to genetic drift. It's a biological concept that essentially refers to randomness in evolution. Essentially, 30% of the population will die randomly, not due to any specific phenotype that they have or any specific characteristic that they have. Just pick 30 out of 100 people and they die due to random reasons. You can see on the graph, it's already updated. It's in the same spot, so it updated the graph, that this doesn't really bode well with the population, especially in the first jump, in the first generation, because we immediately dip. Though, the average reference similarity doesn't seem to be changing that much in its shape, because even in real evolution, we do notice that whenever there is heavy amounts of drift, that though it will be different, the in this case the average reference similarity, or in reality the characteristics that the organisms would have, it does still have a semblance of what evolution is. It does not take over necessarily when the drift is high. 30% is a lot, and I would proceed to run it with a little bit less. Actually, this time we're going to run it with just the criteria. Criteria is a flag for giving your population a natural selection parameter. The way this is calculated doesn't really matter, but we've given it criteria 10. The average reference similarity, it does go up, and there is still that element of randomness to the whole aspect of the code. You should expect that whenever you add a criteria, that the average reference similarity should be better than previously. Specifically, here you can't really tell that it's done a better average reference similarity because of the how many generations there is. There's 100 generations, so the population lived. Now that we have the criteria, the population lives. Previously, the graph was a lot smaller, so you could see the difference in the vertical chains of the average reference similarity much easier. But here, because it's so wide, you can't really tell. Though, it does almost reach 60%. It's at this 50-55 range, which is a lot better than we had previously. Given that, let's run one with just about everything in it. One run to put the rest to shame. Drift, criteria, everything. We haven't really changed much regarding the rate. This has stayed the same, basically the same time, the whole time. But the generations and the size of the population are different. Less criteria than before, less drift than before. This run is phenomenal. 80% reference similarity is really good. You can't expect to get to 100% every time, and honestly, you can't expect the population to live to the end of the run every time. Given that I've tried just about every flag that there is, I'm going to show you what our test file does, and there's 16 tests. That does not mean that there is 16 functions in the program, but there's 16 tests, and it passes all of them, and they are quite comprehensive. That's what we had to tell you today. Thank you for our presentation.